This is Nikita, and I would like to talk to you about rotating things with quaternions in the context of things I learned working with ARKit on my senior project. So some background info. The ARKit is a framework for doing augmented reality applications by Apple on iOS, which makes developing AR apps a lot easier. And my project was all about visualizing sensor data by looking at objects and then seeing a plot of data which corresponds to them. So what kind of problems did I solve with quaternions? Well, this line right here that connects the controller and the plot was something that I had to rotate in order for it to look right, because the way I implemented was with actually a cylinder. So you place the cylinder between the two, and then you just have to rotate it to connect the objects. So we got our coordinates, negative x, negative z, and our y. Our cylinder is there. How do we rotate it? Well, we kind of want to rotate it along y, and we kind of want to rotate it along z. There's different ways to do this. You could use Euler angles, you could use rotational matrices. In my experience, I found that quaternions tend to be more of a consistent experience, and the other methods tend to get, just to me, more confusing as the problem gets more confusing. So what are quaternions? Well, you could kind of imagine them as just being an axis of rotation defined by x, y, and z, and then this last number w defining how much you're rotating along that axis. A little bit more complicated than that, but that's one of the few things you need to know to get by. But if you want to look a little bit deeper to how they're useful for rotation, you only have to think about complex numbers. So if we have a complex number, which is a plus bi, you just think of it as the coordinate. Right here is a, and right here is b, and this is kind of our x or real axis, and this is y or imaginary. And then, so here it is right here. But what's special about this number is it's not just a 2D vector. It's special because it has special algebraic properties because of this I squared being -1, which allows it to distinguish itself from just the normal 2D vector. You say, oh, this 2D vector times 2D vector is what? And then you ask, like, well, what do you mean? Do you mean dot product or cross product? Well, with complex numbers, you just kind of multiply them like a polynomial because it's just actually just one number. So how do we get angles out of all of this? Well, if we just think of A and B as a point over here, then we can imagine we could use trigonometry to find the angle between them. And then this line right here will represent kind of like the hypotenuse, right? Or we could just use Euler's formula to actually do the proper conversion. If you have a plus bi, you can relate this as an angle, which is theta, between this big blue line, which is a magnitude. In this case, the magnitude is 1. It's what goes in front of this e right here. So now that we could think of complex numbers as just this line which travels along this yellow path, and the angle, which shows how far along the path you are, then we see that when we multiply these two complex numbers with theta and phi as their angle, it turns out all we do is just really add the angles together. So if we start with theta and we multiply by this complex number, we just add to this angle. We just add phi, and now we're over here. We've just rotated this much. And if you say that this arrow always has length 1, then you don't even have to worry about the arrow, because if this is 1, this is 1, 1 times 1 is 1, so you don't even have to worry about this. All you're ever doing is just adding these angles together. So what does this have to do with quaternions? Well, if we need two numbers right here to represent one angle of rotation along one axis, then we just need to add two more numbers, and then we get 3 axes of rotation, which is the quaternion. It's just a slightly more complicated extension of what we had before. But it still has all those neat properties where multiplication can give you the rotation along that axis that you need. So how do we get our quaternion in our example? Well, we want to rotate kind of all at once and not do like 2 rotations with 2 quaternions, because you're kind of losing their power right there. And what's also happening is if you rotate once, you've changed the local coordinate system of that thing you're rotating. So when you rotate it again, it's going to be a whole different problem because you're rotating like something that's like totally different now. So how do we get that nice one quaternion along that axis of rotation that we want? Well, we have this vector right here, which is pointing from the remote to the plot. That's just the difference between their positions. And we want to rotate to an axis kind of like perpendicular to that, right? So we could get another vector just by zeroing out the y on that vector. And if you could imagine the plane that those two vectors are on, that's the plane we want to be rotating our cylinder on, so that it lines up nice and connects the plot and the remote controller. Get the angle between the two vectors using trigonometry functions, and then take the cross product of the two vectors. After you take the cross product, you're going to need to normalize it. This makes it length 1, and this makes working with quaternions a lot easier and possible. When everything's 1, everything comes out nice mathematically. And then you also need to, based upon the angle that you have, sometimes you need to flip the output of your cross product to the opposite direction. This is just the cross product thing, and you'll see with experimentation that sometimes, like if your angle is over 90, you get wrong results, and then you're like, oh, if it's over 90, let me just flip it. So that just takes a little bit of experimentation to find out, but after you take care of that, we've essentially solved our problem. That's kind of our quaternion right there, basically. We just converted essentially to a quaternion just using some final math, which is available everywhere. And then once we have this quaternion, all we have to do is multiply it by whatever the quaternion is that belongs to the cylinder, or just set it to be the quaternion that we have right now if it didn't have any rotation previously, and that would be the end of this problem. We would have properly rotated the cylinder. Now, if we take a look at a tougher problem that I've seen, and in this tougher problem, what was happening is I was using the camera orientation to place the display, and when I did this, sometimes like based upon the way I was holding my iPad, it would come out a little bit tilted like you see in the dashed lines, right? So I wanted to make it straight, and I struggled for many hours trying to do this with Euler angles, like trying to decompose it and then seeing like, okay, let me fix just this axis. So it turns out the problem is extremely simple if you just use quaternions. We start by thinking about what is our current orientation and how do we want to fix it. Well, we have our local reference system for the plot, and the green vector is the unit z vector, which points out towards us. This must be the vector we care about because that is the axis of rotation which the plot is tilted on. That's the blue dashed line which represents the tilting in that axis. And we know we have some quaternion, and we don't know where it's pointing to, but we do know that some of it must be pointing in the direction of the green vector, otherwise we wouldn't have this tilting. So we use a method called swing twist decomposition. And so it turns out like you could think of rotating as just having a swing along this axis and having a twist along this axis. And you could take it apart and decompose it into these two motions. So what we do here is we just get the twist, because we don't care about the swing right here. We care about this twisting, which is essentially this tilting of the plot along the z-axis. So we know that we must have some of our quaternion in this direction. So what we do is we project it onto the unit z vector. We end up with this piece of quaternion right here pointing in this direction, which represents this twist right here, this tilting of our plot. If we go to complex numbers really quick, we're reminded that when we multiply two complex numbers, we add their angles together. But we also have to realize that when we think about these complex numbers, there's only one axis of rotation. It's this angle between this number, and we just rotate along this axis right here. If we wanted to, we could say, oh, this is the z-axis. Because there's only one rotation happening here, and these complex numbers, they're always on the same plane or axis of rotation. Another interesting note is the imaginary number we have on top right here. If we do something called taking its conjugate, we essentially flip it over the real line or the x-axis to down here. And that's all taking its conjugate does, is it kind of like flips it. You switch out the I with negative I, and you flipped it over. And this is interesting because if you think about the angle over here between the real line and the top number, it's the opposite of the angle down here of the conjugate. So if you multiply two complex numbers together, you add their angles together. And if you multiply a complex number with its conjugate, you're adding the negative of its angle, which will zero it out. It will remove the rotation. If you multiply these two together, you will be back right here on this line. So you take the conjugate when you want to subtract an angle. Which is what we do here. We take the conjugate of our twist quaternion, which is in our z rotational axis, and what we get is the opposite of the rotation that which we just dislike. This is the opposite of that yellow highlighted tilt. Now that we have the opposite of our rotation that we're trying to get rid of, all we have to do now is take our original quaternion, which belongs to the plot or the display, and then we multiply them together, which is subtracting away that rotation along the z-axis, which makes it straight along that axis. To summarize, I've talked about two different methods I've used in my project to help me solve problems in rotation, when other methods like matrices and Euler angles were kind of getting confusing for me to use. The first method being using two vectors which are lying on a plane and taking the cross product of them to define that axis of rotation, and then using it to kind of do that nice rotation I want in one fell swoop. And the other method being using swing twist decomposition to isolate kind of components of a quaternion that are lying on the local axes that I wish to get rid of, and then using the conjugate of that quaternion to get rid of that rotation. Quaternions have actually quite nice to use, and not only that, but sometimes they're computationally faster, and they definitely take less memory than using a matrix. So they have a lot of benefits. By explaining these problems that I've had with rotation, I hope to have helped improve your understanding of quaternions